Hello everyone, I'm Andrzej Piszewodowski and I'm going to present you our paper Monte Carlo particle filter formulation for mapless based localization. This research was financed by CAPES and we would like to thank the Laboratory of Mobile Robotics from the ICMC Institute of the University of São Paulo. So, most localization pipelines for self-driving vehicles require high-precision 3D maps, which are not easy or cheap to obtain or to maintain. Also, localization based on odometry requires loop closure for mitigating the effects of drift, which is not always available during the trajectory. So, what can we use from a more human-like maps, such as the OpenStreetMap or Google Maps? So, human maps might not be as accurate as the high-precision 3D maps we have, but they still are easier to build and to maintain. So, the main problem here is how to relate the low-level sensor information as images and LiDAR scans to these types of camera, right? This kind of map. So let's think a moment about this map. So one type of information it provides is the road network. And the road network provides intersections. Intersections are very useful because in most trajectories there are several streets that cross each other, and they occur most likely around 100-meter frequency, right? So still it's not as easy to detect them using images, for instance, either due to occlusion or to the traffic conditions. So what if we could use other elements to indicate that there might be an intersection nearby? So if we think about the stop signs and the traffic lights, they might be a good fit for this purpose, right? Because they occur close to intersections. Therefore, we can model our world as the following. Each self-driving vehicle requires a trajectory in order to navigate. So it requires a start point, an end point, and a set of intermediate points in which the agent must follow. So if we think that the agent is always contained between two waypoints, which we name it way segment, we can represent our state in a minimalist way. So we can reduce our state representation to estimate how much did the agent move in this trajectory. So we have a variable for that, which we called L. So, and if we have the expected trajectory and this offset of the agent L, we can convert it back to the Cartesian coordinates. So all that we have to do is that, okay, we can find, so if we have this L variable, we can have in which way segment is the agent contained. With this way segment, we have the parameters for projecting it back to Cartesian coordinates. So we have the angle with respect to the horizon, and we have the offset between the initial and end point. And that from that we can just project using this simple equation, which is not new or unique, but it's just a clever way to converting our minimalist state representation to world coordinates. So if we represent our state in that way, we have some problems which constrain our approaches for state estimation. The first one is that these conversions are not linear, and we have a map that most likely that will not be linear, and the uncertainty does not follow a Gaussian distribution either. So the usual approaches, for instance, the extended Kalman filter, will not be as suitable for representing the distribution of the state estimation. So we decided using a particle filter, which is more usable for, it's more suitable for representing complicated states, the state distributions. So we had to we had to recompute this formulation in order to check if everything was okay, and how could we apply these techniques for our purposes. So the traditional approach for Monte Carlo localization, we have our probability distribution of our state given the from our trajectory given the control actions and the observations. So it is known as a two-step approach in which we have to sample from the proposal distribution, which we will state later, and weight from a target distribution. The issue here is that we have to have a easy and known proposal distribution to sample, and we have to have a good data association and observation model in order to have this in order to weigh our particles. So in order to sample from our proposal distribution, we have some assumptions that we require. So the first one is that we have our previous distribution from our trajectory, so which is this belief from 0 to t. We must have the new control action ut plus 1, and that this action is normally distributed. Also, that we can consider, since we are tracking the amount of offsets the agent moved from the beginning of the trajectory up to a point, we have to track the x movement from the agent, so we can assume that it follows this distribution. So our goal is to relate our proposal distribution, which is this new state after an action given, to the previous one considering this action. So we can reduce our expression. So after we expand it and applying the product rule and using the assumptions from our Bayes network, we reduce our problem to this set of equations, actually this equation, in which we relate the probability distribution from the movement, from the motion, given this action, and our previous state. In practice, what we do here is that we sum our particles with this mi x and add a noise factor sampled from centered in 0 with this standard deviation in the x direction, since we're tracking the amount of movement in the x direction. Okay, we have our proposal distribution. We've shown that it's not as hard to sample from that. Now we have our target distribution, which is, okay, what we want to estimate our full trajectory given all the observations until that moment and our control actions. And we have drawn from this distribution with this proposal, we want to compute the weight. So what if we expand this targeted distribution using the Bayes rule and replacing the factors that are constant with respect to the state, and applying our assumptions from our Bayes network, which is illustrated in our paper. We have this equation which relates the weights to the observation model. So, okay, we have the two steps that we require for the particle filter, and after that we can resample the particles using a low variance sample. But we've followed this strategy, but other strategies could be followed as well. The final problem here is now, what is the observation model? Because we want to relate evidence of intersections to the map, and with that we want to relate how each particle is related to that observation. So how can we do that? So we modeled in the following way. So each intersection can be detected from a range given from this minimum distance to this maximum distance, and each particle is in a given distance st, each particle k. So therefore, if the particle is within this region, so it might have detected correctly this intersection. So, and in order to perform these detections, we have a detection model which has a sensitivity rate and a false positive rate. So for each particle that is inside this range, we assign this probability in which we have the sensitivity of the model, and the particles that fall outside of this range, we assign a false positive rate, because there might have been detected a wrong detection, and this particle should not be disregarded after this detection, right? So we can summarize these steps by saying that we sample each particle by summing its offset with the new offset and adding a noise factor, and we assign these probabilities, which are the normalized false positive rate and the normalized sensitivity. With these weights, we can apply a low variance sample. So how did we test our approach? So we recorded a data set in our city, São Carlos, which was a 1.5 kilometer track. It was a cloudy Sunday afternoon, and it actually had the usual urban traffic. So there's some cluttering, and well, this data set is available online with the code as well. We used our intelligent vehicle Carina 2, which is provided from a Bumblebee XP3 stereo camera, a Septentrion Aster X GPS. We also have the XM's IMU and a Velodyne HDL laser scanner, which was not used for our experiments but recorded for posterior usage. How we computed our ground truth? So we computed the stereo visual odometry using the RTAB map implementation, and corrected using our GPS measurements that have RTK corrections. These were fused using the extended common filter implemented as a ROS package in the robot localization package. So the metric we used for our evaluation was the distance from the ground truth, and we compared 4 different experiments: the visual stereo inertial odometry only, in which no global corrections were performed; the GPS approach only; our proposed method; and our proposed method fused with stereo odometry using the extended common filter. So we had for the stereo odometry without global correction an error over 1 kilometer, while when we fused our approach with the stereo odometry, we reached a 5.9 meter accuracy, distance of close to 5.9 meters. And when not fusing with the extended common filter and the stereo odometry, we reached a 6.4 meter distance to the ground truth, average of course. So we were able to estimate the trajectory, but in this square over here we had some issues because the stereo odometry was drifting and the vehicle was actually stopped in a traffic lights. However, the rest of the trajectory is consistent to what we obtained, and most of the trajectory was below 8 meters from the ground truth, which is close to a commercial GPS. And the filter was able to correct all the drift from the stereo odometry, and we have to be careful with this observation model. We could use a better observation model for our approach, and we can see that this approach did not require a previous mapping step. Also, the maps are lighter than 3D point clouds, and these maps can be easily corrected online, and we did not run into any loop closure in our approach. Finally, we stored our code in GitHub, so anyone can access it, download, use, and run our demonstrations. And we have some improvement directions, like we can have new measurement models for improving the detections, and we should find some way to adapt the model to consider the case when the agent is not in the trajectory anymore. We should consider other features that could be useful for highways or countryside roads, which do not have as much intersections as the urban roads have. We believe that following these directions we might have a very nice improvement in the accuracy and a more robust approach. So thank you for watching, and any questions you can contact us. Thank you.